Oh.
X for pi over 3. Yeah, I think that should be reversed. Yeah. Yep. So it's on all of the angles. So think like pi over 6 is like the 30-degree angle. And so you're looking at the y value. Since it's sine, looking at the y value that corresponds to this angle.
What would be the 30 degrees?
Pi over 6 and 30 degrees are the same thing. Pi over 6 and 30 is 30 degrees. Just like how 60 degrees is pi over 3. Pi over 6 would be 30 degrees. Okay, so looking at example 1A, where is pi over 6? First quadrant, quadrant 1. What do I know about sine? What is sine going to tell me? It's telling me the y value, so looking for the y value of quadrant 1. In this case, y values in quadrant 1 we know are going to be positive, so don't need to worry about any negative shenanigans. And then what is the y value that we associate with pi over 6? 1/2. Very good. And pi over 6 is closer to 0. It's close to the x-axis. So the x value will be bigger, root 3 over 2. The y value will be smaller. But also, we all know the unit circle perfectly, and so we just know that's it. All right. Cosine of 4 pi over 3. Are we looking at an x value or a y value? X value. And where does 4 pi over 3 live? Quadrant 3. And so we know that the x value is going to be negative. Okay, so we're going to have a negative x value here. And what is the x value that is associated with pi over 3? 1/2. So negative 1/2. All right, one more. Sine of 5 pi over 3. Where does 5 pi over 3 live? Quadrant 4. What do we know? Our sine tells us we're looking for the y value. What is true about y values in quadrant 4? They are negative. And what is the y value associated with pi over 3? Root 3 over 2.
What quadrant is 4 pi over?
This would be, so it's slightly more than 4 over 3 is slightly more than 1. So it would be in quadrant 3. All right, questions with kind of our base use of sine cosine. Essentially taking angles from the unit circle and spitting out x values or y values from the unit circle. Something that is not particularly relevant now, but I do want to make sure that our verbiage is not confused, although I am aware that it is confusing. As a function, the input to our function, the x values, are the angles, and the outputs are what we see along the units. All right, so it's a little bit weird when we're talking about this, but when I say that sine gives us a y value as an output, that is true. It's a y value on the unit circle as an output. But when I say that cosine gives us an x value as an output, I'm not saying it gives us an input as an output. I'm saying that it gives us an x coordinate on the unit circle as an output. So a little bit weird there because we're like taking coordinate information here and then using it as our output when it itself is an input or an output. But just kind of a thing to keep in mind, we are always plugging an angle in and it's spitting out information as it relates to the units. Cosine tells us x information, sine tells us y information. Okay, so this definition that we have of sine giving us information about y, cosine giving us information about x is kind of predominantly, I would say, how we are going to use it in the context of this class. That is not to say that the way that we have been using it up until now with kind of our geometric intuitions is wrong. And in fact, there are going to be plenty of situations where it doesn't make a lot of sense to think of this as taking from the unit circle and spitting out. It makes a lot more sense to instead kind of figure out what's going on with respect to the triangle that these values are going to refer to. All right. So number 2 says, let sine of theta be 2/3, where theta is a second quadrant angle. And we are looking first for what is cosine of theta. So looking at this information, just right off the bat here, if we're saying that sine of theta is equal to 2/3, do I know anything on my unit circle that would help me figure out what that theta would look like? Not really. 2/3 is going to be some weird, bizarro angle that's not going to be super helpful for us. And so we're a little bit stuck here, just as far as like how to approach this if we were to try and use the fact that we're saying that the y value on the unit circle is 2/3. It's not going to help us find the x value. So instead of trying to figure out what theta is, let's instead try and figure out what this would be telling us with our kind of triangle information. Okay, so we're thinking of how can we construct a triangle such that sine of theta is equal to 2/3. Got here some kind of triangle. We're always going to have, this is a right triangle, we'll call this theta. And what do I know about this theta? What ratio have I been given? Okay, so I've been told that 2/3 is the ratio of what over what? Opposite over hypotenuse should be equal to 2/3. Now, there are an infinite number of triangles that I can draw that will have that ratio. All right. A fantastic example of that is if we're assuming that we're on the unit circle and our hypotenuse is always just going to be 1, what is the other side of my triangle going to be? What's my opposite side going to be equal to? Just 2/3. It's just that sine value. Right, try opposite over hypotenuse. 2/3 over 1 is just 2/3. But that is far from the most natural way to set up this triangle. What's a much more natural way to go about building this triangle? I think anyway, it's much more natural. When you first look at this, what do you think is the opposite side? What do you think is the hypotenuse? Opposite is 2, and the hypotenuse is 3. For this particular thing. And both of them are correct. Both of them will get you viable outputs for cosine. There isn't a right or wrong answer. All right. It doesn't really matter. It's is ultimately the teal here. Notice the only thing that's really different here between or not the only thing, but a key difference that I have between these two triangles, my radius is different. That value of r, that hypotenuse, is going to be longer. And we'll kind of see how that plays. Or we've already talked about how that plays with the x being our cosine, y being our sine. But we'll see that play out here in a second. Regardless, I am missing my adjacent side from both of these triangles. I need to find that adjacent side, and our methodology for this is going to be the exact same. Regardless of which triangle we use, it does not matter. So I have two sides of a right triangle, missing one. How do I find that third one? What tool do we have in our tool belt that will allow us to find A here? Pythagorean theorem. Okay. I think the numbers maybe look a little bit cleaner if I use this whole number one. We certainly could do the exact same thing with this triangle that we have here, and you'll get the exact same result. So it does not matter in this case. But this tells me that a squared plus 2 squared should be equal to 3 squared. A squared plus b squared equals c squared. Or that a squared is equal to, or sorry, not a squared is equal to, jumping the gun, a squared plus 4 is equal to 9. Subtracting 4 from both sides, taking the square root, I get that a is equal to plus or minus the square root of 5, because we took the square root of both sides, so we get that plus or minus. But in the context of the side length of a triangle, which one of these doesn't really make all that much sense? Having the negative side length doesn't make all that much sense. Now, in the context of the fact that we are in quadrant 2, we actually are going to have a negative side length sticking out in the negative direction. The way I like to do that, though, is I kind of compartmentalize. I treat the triangle as just like its own piece of geometry, and then I just apply the positive or negative depending on what quadrant the theta is in, just so I'm not like confusing myself with positive or negative side lengths, because that can get obnoxious, and I don't want to do that. So I would probably go ahead and say here that a is equal to the square root of 5. And so what is cosine of theta going to be? Root 5 over 3, except what do I have to remember about theta? Theta is quadrant 2, cosine quadrant 2 going to be negative root 5 over 3. Okay. Now, if we were on the unit circle, this would absolutely be the x-coordinate that we're looking for. Right? But are we on the unit circle? And we look at B, and B says, well, actually, we're not on the unit circle. We are instead on a circle that has a radius of 6, and we are trying to find the x value and the y value. Good news for us, though. The process of taking the unit circle coordinates and the actual circle coordinates, converting them, super straightforward. What is it that we do? Not divide by the radius, but we multiply by the radius, multiply by 6 here. So the x value will be r cosine theta, r times that cosine that we found, y value, r times that sine value that we found. So x equals r cosine of theta, which is 6 times negative root 5 over 3, and y is r sine of theta, which is 6 times 2/3. For my x value, I get negative 2 root 5, and for my y value, I get 4. And so the coordinates x comma y, negative 2 root 5. Alternatively, what we could have done, and this is totally fine, if this makes more sense to you than just jumping straight to the end of the formula, we know that x over r is cosine of theta. We know what r is 6. We know what cosine of theta is, we just found it. So x over 6 is equal to negative root 5 over 3. And we're solving for x here. I think this might have been what Sumaran was hinting at, where we're dividing our x coordinate by 6. So we multiply by 6 on both sides to get that x is equal to negative 2. That is also perfectly acceptable. It's the same thing, right? We're kind of doing the solving before we plug in with the other way. But if you want to just use the fact that cosine of theta is opposite over hypotenuse, or not opposite, adjacent over hypotenuse, adjacent is x, hypotenuse is r, solve for whatever you're missing. And of course, you do the same thing. Okay, so key takeaways, sine and cosine, they take in angles. Sine is going to spit out y values that correspond to the unit circle. Cosine is going to spit out x values that correspond to the unit circle. And when we're not on the unit circle, the way we adjust our sine and cosine to be more general is we just multiply by whatever that radius is that we are getting. Something that we are going to look at in Unit 6 is the idea that this radius that I'm talking about is really the distance between where I start and where I end. That r is literally the distance formula, which should come as no surprise because distance formula and circles are very, very intermatched. It's the same thing. Okay? We looked at that way back in Unit 1, where this idea of distance and this idea of what is a circle are so thoroughly overlapped that their equations are literally the same. So any questions here from 4.2? Science. We've got a good chunk of time left. I wanted to open the floor for any general questions, in particular about the classwork. I had a few people from my first and my fourth, but a couple of questions that they wanted to go over from the classwork. So now would be a fantastic time for us to kind of ask, are there any questions that or maybe being a little bit tricky that we wanted to discuss now. I think 14 was a bit of a hot topic for first and fourth. So if we would like to go over that, we certainly can. If there are other questions that we would like to go over, I'd be more than happy to. Now is the time to ask. For today, yeah, it's 14. Yep. Okay. Well, you guys can take the rest of this time to work on the classwork. For extra credit for tomorrow, whole thing finished because we're now done with 4.1 and 14.